Alright guys, so this is the start of the second video of this section of 10.1, and the first one I know is kind of boring, there's just a lot of vocab. This one will finally get into some more mathy type stuff, but we do have a little bit more vocab first, but then we'll get into more mathy stuff, which hopefully is a little more exciting. Okay, so a couple more vocab. So tangent circles would be coplanar circles that intersect at one point. So some of you are wondering how. Now I'm going to try. So here's a circle, and here's a circle. Say they intersect at this one point right here. These would be tangent circles. They don't overlap. They just come together at one point and then go away. Okay, so think of like an infinity sign or an 8. All right, so concentric circles, okay, are coplanar circles that have a common, or I can put in parentheses, they have the same center. Okay, so think of like a bullseye where you have like one around another, around another. All these circles have the same center. Okay, so they would be considered concentric circles. All right, a common tangent now. A common tangent is a line or a segment that is tangent to two coplanar circles, okay? And we'll do some examples here to kind of show you what that is, okay? A common internal tangent would be a common tangent that intersects the segment that joins the center, or that joins the centers, maybe I should say, of the two circles. And once again, we'll do some examples here in a minute to kind of explain it. All right, now the opposite of a common internal tangent, as you could probably guess, is a common external tangent. And this is just a common tangent that would not intersect the segment that joins these centers of the two circles, okay? And once again, we'll see an example here in a sec. All right, so here's a bunch of examples. Okay, now I'm just going to draw this imaginary line that would connect the centers of the circles. Okay, so here's an imaginary line. Okay, so it says use blue to indicate a common external tangent and red to indicate a common internal tangent. So an external tangent here would be this line that's tangent to both of these circles. So this is tangent to both of these circles. I know it's not perfect. Okay, and it does not cross this imaginary line that we highlighted. Okay, so there'd be one common external there, and we would also have a common external down below here. Okay, so we would have two common external tangents. Okay, and on B, it would be the same way. If I can draw a straight line. Let me try that again. So it'd have to be slanted a bit. So here and here would be one. And then here's another common external tangent. And once again, these are common externals because they do not intersect this line. So on C, I want you to go ahead and draw, there's two of them, draw the two common external tangents on C. All right, so just like the other one, you have one on top and one on bottom, and they're common externals because they don't pass through this imaginary line that connects the centers. All right, now let's look at common internal tangents, okay? So common internal tangents will pass through this yellow line, okay? So if I look at this, and this is going to be hard for me to draw in here. Let's try that again. Okay. So, there we go. That's better. Not perfect, but you get the point. So that's a tangent, and this does not look like a tangent, guys. That should have been a little steeper. Right there, that would be a common internal tangent. Once again, it's a common tangent because it's tangent to both of these circles. but it does cross through this that joins the centers. And then if I draw the other one, it would be somewhere, hey, that's a better one, right here where it's tangent here and here. That would be another common internal tangents. Okay, this one here, we would only have one common internal tangent, and it would be right here. Okay, on here, there's no way that we could draw a common tangent because these overlap here. That would also cross through here, so I would have 0 internal tangents. All right, let's look at a couple theorems, do some examples, and then we'll be done with this section. Okay, so theorem 10.1, tangent line to a circle theorem, tells us in a plane, a line is tangent to the circle if and only if the line is perpendicular when you draw the radius. Okay, so we know that this is tangent because of this right angle here. Okay, coming from the radius to the point of tangency, it will cause a right angle if this is tangent. If this is not tangent, this will not be a right angle. Okay, and theorem 10.2, the external tangent congruence theorem, if RS and ST are both tangent to the circle, then RS is congruent to ST. Okay, that's all this theorem tells us. All right, so let's look at example 3. Okay, it wants to know, is ST tangent to the circle? Okay, well, it looks tangent, but we cannot go by looks. Hopefully you've learned that so far. All right, so from theorem 10.1, we know it's tangent if and only if it causes a right angle where the radius meets it. Okay, so if this is a tangent, here's the radius. If it's tangent, that means that this has to be a right angle. Okay, well, how do we know if it's a right angle? Well, we look at this triangle here. Okay, if it's a right angle, then it has to satisfy the Pythagorean theorem. And if it's a right angle, then this is the hypotenuse, the 37. So I want to say, is 35 squared plus 12 squared, is that equal to, and I'm going to put a question mark because we don't know, 37 squared. Okay, well, 35 squared gives me 1225 plus 144. Is that equal to 37 squared, 1369. I'm going to put a question mark here. 1225 plus 144 is 1369, which equals 1369. So Pythagorean theorem holds, yes, this is a right angle, and therefore, yes, ST is tangent to, once again, this is circle P. All right, let's look at example 4 now. It says, in the diagram, point B is a point of tangency. So if it's a point of tangency, that means this has to be a right angle. Okay, find the radius. Okay, so once again, we're going to focus on this triangle right here, and it's a right triangle. Okay, and here to here, this side is just 50 plus r. Okay, and that would be my hypotenuse. So I could say 80 squared plus r squared has to equal 50 plus r squared. Okay, so 80 squared gives me 6,400 plus r squared equals, and remember, 50 plus r squared equals, and I'm going to flip these around just because it makes it easier for my brain, r plus 50 times r plus 50, right? And then we would have to FOIL it. Okay, so when we FOIL that, we get r squared plus 100r plus 2,500. Okay, now if we do some math, minus r squared on both sides, don't freak out, because the r squareds end up going away, so 6,400 equals 100r plus 2500 minus 2500. So I get 3900 equals 100R divided by 100 divided by 100. 39 equals R. So my radius has to be 39. All right, last example here. Okay, RS is tangent to circle C. So RS is a tangent and RT is a tangent. And as we know by that second theorem we did right here, if both of these are tangent, then they're congruent. Okay, so because they are congruent, that means they have to be equal in length. So I can say 28 has to equal 3x plus 4. Now it's simple algebra, minus 4. 24 equals 3x divided by 3. 8 equals x, and that would be our final answer.